So welcome to the virtual lab for fractionation. Now I'm going to be honest with you here, and my honesty is going to come through like this. I hate this lab. I hate it. I cannot stand it. And most of the time, students can't stand it either. Now here's the reason why. The point of this lab is to test your patience, I fully believe. Because this lab takes forever. Forever. It's one of those labs where you come into the lab for that day and you better come early in the morning and you better be prepared to stay until the end of class time or even later, depending on how fast you can get these things to go over. And you'll see that in the time and date stamps that I have to show you throughout this process. The lab itself physically is not difficult. The only thing I have to do is heat up a solution and collect it into a collection vial. That's it, folks. That's all that I have to do. And then at the end of this, I run it on Refractive Index and I run it on the Ftir. But the process of getting those collection vials with 2 to 3 milliliters takes forever, hours up on end. And that's why people cannot stand the lab, right? So it's okay. It's one of the things that we've got to deal with. It's one of the things that we have to do. And it's also one of those labs that if I did not have to do it, I would sit back and laugh at you and snicker while you were doing this process. But this year, if you're watching this in a virtual lab, well, I probably won't be able to do that. The joke's on me now, not on you. All right, so let's talk about the pieces and parts that make this thing work. First is a heating mantle, as you can expect. So what we decided to use here was a 250 milliliter size heating mantle, because I was getting ready to use a 250 milliliter boiling flask. All right, what's up next is, of course, a variac. If I'm using a heating mantle, I have to have a variac. I can't just plug that heating mantle directly into the outlet because it's going to overheat and I don't have control of the temperature. So this, of course, supplies the heat source. A couple of things I want to tell you about it. I know that I've showed you this picture a couple of times, but make sure that this is off before you actually plug it in. You'll see the power button down here in the bottom left-hand corner. Just make sure that that is off, because if not, and this is on, and you directly plug it up into the outlet, you could blow a fuse in the variac, and the variac will be down until we replace the fuse, and that's really dependent on if we have extra fuses or not that make this thing work. So just make sure it's off before you plug it in, and then you can turn the power on to the variac, and then you can dial up to whatever temperature that you need or whatever voltage supply that you need. All right. So the meter, of course, on the front. If you get some of these newer ones that are reddish in color, you'll actually see an analog meter that's here. This typically needs to be in the greenish area, and this will let you know that you are supplying voltage to the heating mantle. The reason I like these on the newer ones is because some of our older ones do not have these. And students have a tendency to plug these up and just assume that they work. And they crank the temperature up on these things, thinking that the heating mantle is going to get heated up, and it does not. So at least if this meter is working and we're in the green area, it is a sign that this is supplying the needed voltage to your heating mantle when you get to that point. So that's why I really like the red ones over some of the old ones that we have. All right, other pieces to the fractionation. We've got a Vigru column and a drip adapter. The Vigru column you've seen before. You've seen this in the ethanol lab, which is why we start off with that one before we introduce this one to you. So the Vigru column is going to make its presence again. You know how that process works. You know how it's structured. You know how it's made. Same kind of deal, same kind of scenario for the ethanol. Drip adapters were also used for the ethanol fractionation. Remember, look at what I said. Ethanol fractionation. That's what we did back then. And the drip adapter is to the right-hand side in that picture. So just a nice little piece of glassware that takes all of the condensate from my West condenser, and it just funnels it down into a collection container that I have down below. So Vigru column, drip adapter is going to be important. As with the fractionation with the ethanol, we also had a West condenser. The West condenser you're going to see on the left-hand side. And we also need to keep track of temperatures throughout this process, and more than one temperature. So this is where this gets a little bit different than the ethanol fractionation, because I've got two thermometers here, not one. The first thermometer is going to go into what we call the pot, and the pot is the area that's going to have the sample from the very beginning. So my sample is going to distill from the pot, and it's going to go over into the collection tube. So we want a thermometer in that pot. We want to keep track of that temperature that's happening inside of my boiling flask that has the sample in it. The other thermometer probe, the second one, is going to go to something that we call the head. And the head is at the top of the Vigru. So I'm keeping track of two temperatures here, and you're going to see that throughout this presentation and throughout this process. For that reason, I need multiple accesses into the boiling flask. So what we decided to use here was something called a triple neck boiling flask. Triple neck because I'm going to put a thermometer into one of them, and I chose the one over here to the left. So the thermometer is going to go in, and it's going to go down into my liquid solution that sits down below, and then the middle one is going to be my Vigru. So the Vigru column, the fractionating column, is going to be there just like it normally would have been if, again, this was the ethanol fractionation. That's where we put it in the center. And then over here to the right-hand side, this is just an access point. That's all that this is. So what we like to do for this lab is to prepare the samples fresh. And we don't want to mix these prior for you coming into the lab to actually do it. So this will typically just get a plug, just some kind of stopcock there on the top, some kind of cap that we will put onto that joint. And the reason for that is because I can easily take that off, and then I can put the sample down into the boiling flask without disassembling everything else that needs to go on. So this is the reason that we have a triple neck boiling flask for this particular type of experiment. These boiling flasks have single necks, which was what we've used before. They do have triple necks like you're seeing here. They have double necks as well. Sometimes you don't need that third access point because maybe you don't need a thermometer in there. So 2 would be okay instead of 3. We don't have these in our lab. We think that this is kind of useless. So we get triple necks and we get single necks, and that's about it. All right, some other pieces and components to this whole assembly. I've got some rings to the right-hand side. Those rings, of course, one is going to hold up my heating mantle, and the other one is going to hold up my collection vial or my graduated cylinder in the ice bath that we'll see a little bit later. So that's why I brought out 2 of those. To the left-hand side, you're seeing a lot of clamps. So these clamps, of course, are going to help secure my whole entire assembly once it gets together. I don't want this thing to topple over, and those little clips are not going to do justice for me, right? They're extra security, but it's not going to hold it all together. So the clamps are going to hold up my Vigru column. They're going to hold up my boiling flask. It's going to hold up my West condenser and so forth. And you'll see those in the final image finally that I'll show in a couple of minutes. All right. Other things, wire gauze. Wire gauze you see over to the left-hand side. The wire gauze is going to serve as just really a platform here. That's all that this is for. And the platform is so I can put an ice water bath on top with a graduated cylinder inside of that. So if I don't use a wire gauze, how am I going to hold it up, right? We either have rings or clamps. And if I have a ring, then it's going to fall right through the ring. So I need a wire gauze to sit on top of the ring so that way my stuff doesn't fall through. And then over on the right-hand side, these are just collection vials. So once I siphon off 2 or 3 milliliters at a time, I'll record the volume of that collection, and then I'm going to immediately, because these things are volatile, I'm going to immediately pour that component into a collection vial that you see there, and I'm going to put a cap on it. So that way I can set this to a side. It's not going to evaporate. It's not going to change composition. Everything will go according to plan. Knock on wood, I hope. All right. I keep talking about the ice water bath. Here's a picture of that, of course. The ice water bath is very important in the beginning. Not so much toward the end, though. And here's why. We have a 3-component system. I've got acetone, I've got cyclohexane, and I also have toluene. All right, well, toluene has a boiling point of 110 degrees, give or take a little bit, okay? So I don't think necessarily an ice water bath is going to be so drastically important with the later cuts. However, with the acetone has a super low boiling point. So there is a chance that if I start distilling acetone off and I start collecting that in small increments, the acetone will evaporate on me, and I have to make sure that it stays cold. If it doesn't stay cold, it will evaporate and I will lose volume throughout this process. So ice water bath, very important in the beginning, but not necessarily toward the later stages of the fractionation. I would be okay if I just put a graduated cylinder up underneath there and just collected my fraction as it came off. Now, if you want it to use the ice water bath the entire time, then go for it, right? That doesn't really change the process or anything. So keep it cold, keep ice cubes in there, keep your graduated cylinders in there, be my guest. Go for it, if that's what you want to do. But for me and for this particular lab, I did take that ice water bath away toward the later stages of the fractionation. And you're going to see, hopefully, that my data was not really tremendously impacted by that. The collection containers are just simple graduated cylinders. These are 10 milliliter sizes. The reason I chose the 10 milliliter size is because the lab directions tell me to take off 3 to 4 milliliters, and it might even say 2 to 3 milliliters. I forgot what it is, actually, but it's one of those. It used to be 3 to 4, and maybe we changed it to 2 to 3 to get smaller ones. So if it's 2 to 3 mils, 3 to 4 mils, I don't need anything bigger than a 10, and the smaller the better. So I chose the 10 milliliter graduated cylinders for that reason. All right. So now what I want to do is show you a video of the actual setup and all the pieces and the parts that are really hooked together in the proper order. So just bear with me for a few seconds and I'll play this video for you. Guys, here's my setup for the fractionation that we're going to be doing with this 3-component system. So what I've started here is my variac transformer, of course, that's going to supply the needed energy to, guess what? You know the drill, a heating mantle. Inside or on top of the heating mantle, you're going to see my boiling flask. It's a triple neck boiling flask this time. And on the inside, you see my unknown already. So you can make observations of that unknown as you want, but you can see it's very clear. It looks like water. There's no color. I can see right through it. Up through the triple neck, I'm going to see a thermometer adapter over here to the left-hand side. I see a cap that I'm going to be using because I needed access to that boiling flask on the right-hand side. And then as we go up, I begin to see my fractionating column. My fractionating column is there for a purpose. Hopefully you'll know why we chose the fractionating column. And then at the very top, you're going to see a thermometer yet again to measure the vapor that's getting ready to go over into my condenser. All right, next is the condenser, of course, with my water out location in the very top. And then toward the bottom of that west condenser, I see the water in. So that means this has to be hooked up to a faucet. And I've got my drip adapter. The drip adapter is going to lead into a graduated cylinder. That graduated cylinder is going to stay cold, so I'm putting it into an ice bath. That way my component does not evaporate on me by the time I transfer it to a container. So all in all, there is the fractionation setup that you're seeing in the lab needed for this experiment. Okay, so as you can see, this setup, it's not simple as far as, just throwing it together in 2 or 3 minutes. It does take a little bit of effort. I do have a lot of clamps that I have to work here. I've got a clamp here, as you can see, on my triple neck, holding it up. I also have a clamp on my Vigru column or my fractionating column that's here. I also have a clamp that's at the top here that's holding up my West condenser. And then here I've got a ring that's also holding up my ice water bath, as I've mentioned before. So it does take a little bit of effort. It takes a little bit of time to set this up. If we were actually doing this in person, I would be really nice and I would have this set up ready to go for you. All the pieces and components are there in one location, and you would just have to kind of attach the things to the metal rods and so forth. But everything would be nice and convenient and organized for you. So with that said, there's the setup for the fractionation. If you want a different angle or a different picture, here it is. It looks like the countertop's kind of disgusting. Shame on me, right? But sometimes that's just how a lab is. But there is a different angle or a different perspective of the fractionating column. Notice that over here to the right-hand side, I've got my collection vials that are ready to go because I'm going to be collecting right here. And as I'm collecting, I want these very convenient for me. And I also did more than one graduated cylinder. I did a total of 3. You can see the other 2 that are right there. The reason I did this is because I don't need to lose any drops along this process. So when I take this graduated cylinder away, I need to replace that one immediately with another graduated cylinder so that way it can continue to collect the drops as they're coming off. So I need some backups, and I did 3. The reason is because when I take this one off, what would happen if I grabbed this one and put it up and accidentally dropped it and cracked it, right? Then what would I do? I can't stop the fractionation. It's going to continue to drip, and then I don't have another backup for that backup. So I did 3, and I did rotate all 3 of them, but that's one of the reasons that I do that, right? It's better to be double safe than just safe. So I brought in over an extra. Here's the front side. Again, this is going to be something that's very similar to maybe what you would see on a test or some kind of lab practical and so forth. All the pieces of the components labeled and identified. What are they called? So I've got my heating mantle and my triple neck bowling flask, my Vigru column that goes up, my thermometer adapter on the head, my thermometer adapter down here on the pot. Then I have the West condenser that goes across. I have a drip adapter that goes into a graduated cylinder that is contained in an ice bath on that side. All right. The 3-component mixture. Well, what are those 3 components? I can tell you, I can identify what those are, but I'm just not going to tell you how much is actually there yet. I know how much each one of these have that I put into that sample because I made it. You don't. That's the purpose of the lab. So the very first one is going to be acetone. If you wanted to know the structure of acetone, this is a C double bond O, which we call a carbonyl in a laboratory environment. And there is something that we call a methyl group to the left and a methyl group to the right. So C double bond O, CH3, CH3. So there's the structure of acetone. It is the lowest boiling point out of the 3. Therefore, this will start to fraction off first. It will turn into a vapor first. It has the lowest boiling point. It will go up the Vigru column first because it's got the lowest boiling point. It will condense into the condenser because it's made its way up to the top first. And then that is the very first maybe handful of fractions that come off depending on how much I've used of that. So I've used a certain amount of milliliters of acetone for this unknown mix, and your spreadsheet and our lab data together will hopefully get really close to that value that I've used. Cyclohexane is next. Cyclo means a ring and hexa means 6 in a laboratory. So I've got 1 carbon, 2 carbon, 3 carbon, 4 carbon, 5 carbon, and 6 carbons. So 6 carbons all the way around. There you go. There's cyclohexane. It has the middle boiling point, so this would be coming off second, and this would be the second component, of course, that I would be collecting in my fractionation column. However, when saying that, you need to understand that it is very hard sometimes to get super clean cuts. So that means that if cyclohexane begins to fraction off, I can probably expect that there might be a little bit of acetone still with that, right? Or if this is in the middle, and let's say that I really crank the heat up on this sucker, then there could also be some toluene that's going to be mixed in with that cyclohexane as well. So this is just one of the common problems that we have in the middle boiling point areas, not the lowest and not the highest, of course, right? So cyclohexane, don't be surprised if we don't get a completely super clean cut there. Finally, toluene over to the right-hand side. The structure of toluene is going to be a 6-membered ring, just like cyclohexane, but there's an alternating single, double bond all the way around. Sometimes we abbreviate that with a just simple drawn ring in the center that represents a double, double all the way around it. And then off of this ring, we have a methyl group, so a CH3 group. This has our higher boiling point out of the 3 components, but, you know, that will come off very last, of course, and I probably would have better luck getting a pure component out of that one as well, just because it is coming off last and nothing else is going to be there with it. Okay. As far as lot numbers go, right? I mean, label information and that type of thing. As far as the label information, these are the 3 jugs that will be used from this point on for everything. So, meaning, these were the 3 that were used to make your unknown. We also will do a refractive index read later on. That refractive index read will include all 3 of these components from these jugs just as they are. And then later on, we're going to do FTIRs as well. So the infrared spectra will also come from all 3 of these. So these are the 3 components. The acetone is going to come from a company called EMD, in case you need the manufacturer number. The cyclohexane is going to come from a company titled Alpha Acer. And the toluene is going to come from Fisher Scientific. As far as the lot numbers go, well, we can worry about that a little bit later if you're okay with that. The lot numbers, I need to zoom in a little bit closer on some of these labels. Cyclohexane, it's right there, very front, very center. But where's the lot number on acetone? Where's the lot number on toluene? So here I'm going to have to zoom in on the labels and kind of show you that information. And I'll do that a little bit later. But right now, we are just getting our unknown component that someone else has made for me, or in this case, I've made it for myself, and then I've given it to myself. And we're going to take these 3 components. We know those are the 3 components, and it's up to us to start distilling them. All right, so I put that unknown mixture into my triple neck boiling flask, and here it is. So that way, if you have to make observations of your unknown, this is a very close-up picture of what that begins to look like. It's very clear. It looks like water, right? It also has a very strong smell. You know, if you can imagine the smell of acetone, which is fingernail polish remover, and if you can imagine the smell of toluene, which they do sell in the hardware store as various solvents and keep it in the paint counter areas and stuff, you can imagine what this stuff begins to smell like. So there's a very strong chemical odor that comes from it, but acetone, believe it or not, overpowers the majority of it. It is super strong with this 3-component mix. All right, so now that my component is inside of that triple neck, I then put the cap onto that 3rd neck, right, to seal it off. I don't want to lose anything through the evaporation stage. And I'm going to turn my variac on. So I'm going to put the heat source finally onto this triple neck flask. So what I do is I flip it on, and I take the dial, and I dial in to about 70. And right here's the time that I began that morning. It was 11:29 a.m. So I started off really low. Imagine this is your stove eye, and you're going to start off very low on low heat. And that's what I've done here, right? I don't want to go too fast. I don't want to crank this all the way up and get this super hot, because if I do that, the whole point here is to get these components separated from each other. And if I rush the process, I'm not going to be able to fully separate anything, right? It's going to be a major problem area for me. So with that said, I started off on 70. All right, so I'm going to record some temperatures with this process as well. This is one of those settings that I'm going to have to record for my lab notebook, because this is the variac setting that I began with. I'm also going to have to record times, so that time is also very important for my lab notebook, and I'm going to have to record temperatures. All right, so this is the temperature. Anytime you see the picture that's going to be angled like this, This is the temperature of the pot sample. And right now, as you can tell, I mean, we haven't even hit the 50 mark yet. And if that's 50, then this is going to be 49, 48, 47, 46. We probably haven't even hit the 45 mark yet. So on the lab notebook, I can write less than 45, because really after that point I really can't see down into that neck very well. So less than 45 is going to be okay with me. As we start seeing temperatures, we can start recording those actual temperatures, but I can't lie about it. So what I see here is less than 45, and that's just going to have to be how I report it. I'm also going to see another temperature on every single one of these cuts, and this temperature, anytime you see the thermometer going straight up and down like this is the head temperature. So this is at the top of the Vigru column. Well, right now, here's my 30, and that's 29 and 28 and 27 and 26 and 25 and 24 and 23. So I'm just going to have to write less than 23 here. The reason I can't see down into that neck from this picture, and I can't lie about the data. So if I start seeing thermometer reads, then I can start reporting actual numbers. But until that time, I'm just going to have to put less than and be okay with that. Right? As this triple neck begins to heat, this is what I begin to see. So it doesn't take very long in order for it to get to this point. That's not surprising. Acetone boils off at a very low temperature. Hopefully you know what that temperature is if you did your background work already. And inside of this triple flask, I'm starting to see some condensation. Okay, but one of the things that I always look for are things changing. So is that sample looking different as it begins to heat? Or is the sample beginning to change on me in any form or any way as my components are beginning to evaporate and leaving that three-component system? So again, you can make those observations as you see fit, but there is the picture of the triple neck with the initial stages of the condensation that begins to happen. When this condensation begins to happen, I then look back over at my thermometer of the triple neck, or my pot thermometer. And my pot thermometer skyrockets, and this is where it goes. All right. So this is as the condensation is starting to form, as my first component is starting to heat up and starting to evaporate off. This is the temperature of that pot sample in the initial stages of the fractionation. So notice what it was in the very beginning. And now we can clearly read and identify what this temperature is. Notice that each one of these marks, this is 60, this is 61, 62, 63, 64, 65, 66, 67, 68, 69, and 70. So this thermometer is calibrated to 1 degree differences. So you can kind of eyeball and estimate that temperature there for your lab notebook if needed. But that is the pot temperature of the first fraction that begins to come off. All right. The first drip, now that this is heated up, now that I see condensation, the first drip is very important. I'm starting to see the first drip right now from my Vigru column. It's not made its way to the top, but it is condensating back down, and it's falling down into my triple neck. Well, that very first drip is going to be important. I always want to watch out for that. And I also want to record the temperature, or the time, of which I see it. And that happened at 11:36 a.m. So 11:36 was the first drip that I saw from my Vigru that goes back down into the triple neck. Now, I'm also going to record the first drip that I see once it gets to the head. So that is going to be another reference point for me and another piece of data that I need to put into my lab notebook. But right now, the first drip inside of that triple neck is going to happen at 11:36. So you're looking at these times and you're saying, well, that's not too bad, right? 11:29, I turned the heat on. And then at 11:36, about 10 minutes later, I see the first drip. What's he talking about? Why does he say this takes forever? You hold on. You see. You'll see. All right. So now that we've recorded our first drip, I want to play you another video, and that maybe will show you the drips that are beginning to happen. Guys, I wanted to record this video so that way you can see the beginning process of my heating triple neck flask. Right now you're seeing a little bit of disturbance on the surface of the pot, and those disturbances are coming from small drips that I'm beginning to get from my Vigru. So my Vigru is there, and you can see the first couple of drips that's happening from my fractionating column. It's not made its way up to the neck and the condenser yet. It's just now really started, and that is what the observations begin to look like in the boiling flask. All right, that was exciting, wasn't it? Now, so I just wanted to show you, because I don't want you to miss out on any of these steps, is the initial stages of the dripping that begins to happen in the triple neck. And as I begin to heat and as I begin to wait, those vapors will rise up the Vigru, and they will also begin to drip inside of the Vigru. And that's what you're seeing here in an image. You're starting to see a drop getting formed onto the teeth of the Vigru column. And this is a very good sign that it is going up the column like it should, and it also allows me to track it. It allows me to keep my eyes on the condensation, where are the drops happening, because over time those drops should go higher and higher and higher up the Vigru. If they do not, and they never go higher and higher, then that means I need to crank up my variac and I need to supply more heat to that boiling flask that's sitting down below, or I need to insulate my Vigru to help keep it warm because maybe it's cooling down too fast. All right, so here's another video that shows you drips inside of the Vigru column. Okay, so this is the Vigru column, and what you're seeing in the video right now is my condensation ring. Hopefully you can see the movement of those vapors in the fractionating column. It's something that we didn't see with the ethanol distillation because I put a piece of aluminum foil over that column, but here we can clearly see the movement of those vapors and condensing back down. You can see them on the sides, you can see a little bit of wiggle room that's happening there in the Vigru, and that is how I track the vapors that are getting ready to come over. Okay, so if you notice toward the end of the video, it almost disappeared on us, right? We saw it in the beginning and we saw that waviness form. It looked like things were flowing down the sides, and then it just kind of, poof, disappeared. Well, that's because that condensation ring had enough time to go up the Vigru during that recording. So here's just another video of tracking the condensation and tracking the droplets up the Vigru column through the fractionation process. Okay, so my fractionation is getting closer. You can see the movement on the Vigru, the waviness and the glassware toward the top of this image. And it's right below my thermometer right now. So that thermometer is the head thermometer, and I can see that that vapor condensation ring is moving its way up, 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 and it's getting closer and closer to that thermometer. When it hits the thermometer, my temperature is going to skyrocket up, and then it's going to start to venture over into the condenser that's here. Okay, so as you can tell, I was really excited because I was getting ready to get my first collection, which meant that this process was happening kind of fast in the beginning, and I was okay with that. Maybe I wasn't going to be there forever. So the very first drip that I began to get at the top of this Vigru, at that head thermometer, when that condensation ring reached that thermometer and my thermometer went up because my vapors are now up at that point, that very first drip happened at 11:45 a.m. All right, so now I can go back and compare that to the first drip inside of the triple neck to see how long this process actually took for that component to go up the Vigru column. Okay, so with that said, when I did see the first drip at the head, because this is the head temperature that we're focused on right now, this is the temperature at the head. So you can make that reading yourself. There's what the thermometer said. I'm not going to tell you what that says. You're a big boy. You're a big girl. You can read those thermometers just like I can. All right. So I'll let you go ahead and make that recording and make that observation. Okay. So down at the bottom, the triple neck temperature, this is what I begin to see. This is a little bit hard to read. I know that because I see a condensation ring that's happening here inside of that adapter. The blue area looks to be about right there. You can kind of pause this video if you need to, make an estimate of what you see as far as the temperature goes for that particular pot reading, but there's just another kind of piece of data that I can put into the picture. Once the vapor gets to the top, it then ventures over into my West condenser. And the West condenser's purpose is, of course, to condense your vapors down into a liquid. Okay, so here's the problem that I have with the engineering of the West condenser. The way that this is made is that there is a divot, and it's right there. So what I begin to see is a pooling up of liquid that begins to happen right here before it goes over and down into the West condenser. This is going to cause me some problems as far as getting clear, concise cuts. And the reason is because it will be pooling liquid right there at the head of the West condenser. And there's nothing that we can really do about it, right? I mean, you can see a drop that's kind of leaving the Vigru column at this point, so it's condensating even before it gets into the West condenser. So it begins to pool up, and that's where it begins to happen. So over time, as I begin to collect these fractions, if I do have a problem with not getting a clear cut of a pure compound, this could be one of the culprits right there. It is that small little dip in the West condenser that pulls up the liquid, and that liquid will have to kind of get full like a lake before it overflows. And that's always a common problem that we see with the West condenser. All right, here's a picture. It's not a drastic, exciting image, but it is an image of the very first drip that I am getting down my West condenser. So I see the little trail of wetness that this little thing's leaving behind, and then there is the drop, my very first drop of liquid from my triple neck that's made its way into the condenser, and then down this tunnel it's going to go. And I'm getting ready to collect it into a graduated cylinder in ice over on the right-hand side of my apparatus. So the ice bath collection is here. Again, a very must for an acetone collection, and that will be the at least beginning half of the fractionation process. All right, so I've got another video here. I want to talk to you a little bit about the dripping rate. How fast is fast and how slow is too slow. So that's what this video is going to focus on. Guys, I'm recording this video because I want you to see how fast this fractionation is actually dripping. I don't want to go too fast, right? Because it's my job to make sure that these three components are separated. But at the same time, I don't want to go too slow, because if I do, I'm going to be here forever. And I don't want to be here forever, and you don't want to be here forever. So I'm getting a Goldilocks drip right now, which means it's not too fast, it's not too slow, and I can easily change out my graduated cylinders, my ice baths, and everything else that goes through that I need in order to change out without a problem. So I'm not overhauling it, I'm not going too fast. About 1 drop every second or 2 seconds is a pretty good rate as far as the fractionation is concerned. Watching that back, I don't know what an ice bath is, but I know what an ice bath is. But I guess those two words interchange with this southern accent, don't they? All right, so there was the video of the dripping rate. It's about 1 drop per second. That's a pretty good rate for me as far as keeping up with this whole process. If everything goes according to plan, 1 drip per second, then this would be a wonderful experience that I'll get to have with fractionation, but it will not stay that way. All right, so cut number 1. So once I get my first cut, remember the lab directions told me I think 2 to 3 milliliters, somewhere in there. Here's the graduated cylinder, and there is the volume that I have collected. So the head temperature, right, if we go back, this is the head or the pot temperature for that collection. So that is the temperature that I would want to write down for cut 1. And then as far as the head temperature goes, this is the head temperature that I would want to write down for cut 1. We're going to be beginning to write down these temperatures for each one of these cuts that we collect. All right, so for cut 1, there is the volume. So if you need to pause this, pause me, read the volume that you see onto the screen, and then hit the play button when you're ready, and we'll go on and we'll collect the other fractions as we see fit. As far as the time, though, that's concerned, we will report these times a little bit later. I've got those in a different area of the presentation. I didn't want to bombard you with too many data points at once, so you will find the times of these cuts somewhere else in the presentation at a later time, all right? But here is the volume of cut number 1. Notice that these are in 0.2s. So this would be 2.2, 2.4, 2.6, 2.8, and this would be 3.0. So this is 3.2, 3.4, 3.6, 3.8, and then 4.0. You also want to read the bottom of the meniscus, and there is the bottom of the meniscus right there. So keep that in mind when you record these volumes throughout this process. All right, so now I'll go into cut number 2. So I begin to record my triple neck pot temperature, and that's here. So once again, if you need to pause me, put it on pause, write down that temperature that you see, and then the head temperature is going to be there. Okay, so now that you have those two pieces of data, we now need the volume for cut number 2. So it continues to drip, I continue to collect it, and here is the volume that's associated with cut 2. Again, I tell you the time a little bit later on throughout the presentation, not here. Okay, so after this point, I see a tremendous slowdown in the drips. And again, I don't want to wait here forever. So I'm going to have to take my variac and I'm going to have to crank it up. So we now are a little bit past 75. I'm going to say 75 here. So 75 setting on my variac, I begin to heat this process up, and then I take a look at the temperature of my triple neck, which is now here. It's gotten a little bit hotter, as you can see. And then I take the temperature of the head, and it's there. Again, the condensation ring's kind of covering up a little bit, but I think that you can clearly see the blue line, and you can pretty much tell where the 40 mark is at least. So you can use that as an observation or a guide. Well, the problem is that I still don't get drops. All right, so I still don't get drops, which means that I'm going to have to cut the variac up even hotter. So this time I turned it to 80, and I wait and wait and wait and wait, and then I finally do get drops that happen in my graduated cylinder. The pot temperature and the head temperature are the same. They were the same as what they were just a few moments ago. All right, the only thing I did was increase the temperature slightly of the triple neck bowling flask. And here's cut number 3. Okay, so now that you've got that volume for cut number 3, I then continue to heat this process up. There is the temperature for the triple neck, or the pot. There's the temperature for the head. And then cut number 4. There's the volume. So I still don't make any temperature changes on the variac. It's still coming off. I'm very happy with that, right? It's still getting hotter and hotter. Stuff is still coming over and over. So I go back, record the temperature for the triple neck. It's here. I then record the temperature for the head once more. It's there. And then I collect cut number 5. So this is the volume for cut number 5. Again, I had to wait a little bit longer to get the cut, but this process hasn't been as bad as what I thought yet. Okay, so then I go back. I record the temperature for my triple neck. It's here. Hopefully you can see that go up and up and up and up and up. That's what it should do, right? The head temperature, there it is. This will go up only when the component has a higher boiling point. So if it's just acetone that's coming off, well, it will keep it very consistent until acetone completely goes away. Then cyclohexane maybe will come up second. It has the next hottest boiling point, and that vapor will be a little bit hotter, and that's when my temperature goes up. If my temperature goes down at this point, then that means acetone has went off and nothing has reached the temperature yet, and my thermometer's cooling off. So that's a very good sign that I need to crank up the temperature of my heating mantle, or I need to do some insulation onto the Vigoroo, one or the other. But the pot temperature should go up, 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 up. Maybe not with the head. And then finally, cut 6. There is the volume for cut number 6. Okay, so after we do cut number 6, we are ready for cut number 7. I hope I record the temperature. Here is the temperature of the pot. It's almost getting ready to go into that gray area, right, where that rubber stopper's at. And once it does that, I'm going to have to say greater than 90, right, because this is 85, and right there is 90. And I won't be able to read anything up higher than that. So I'm just going to have to say greater than 90 when that happens. But right now I can still record a temperature, a real legit temperature there. All right, so in the next video, or in the next slide, I've got a video. So just bear with me. So here's the story with the pot temperature that you're seeing here. Right now it's getting ready to go up into the thermometer adapter, and I won't be able to really read that after it gets past that point, which is okay. I just make a note of that in the data sheet. At the same time, the purpose of this temperature is to make sure that I keep track of what's happening down here in the pot. Because as this begins to heat, it's going to start to boil, and I can figure out what components are getting ready to evaporate based off of the pot temperature that I'm recording. So for instance, if my pot temperature is just 50 degrees, it's a very good sign that toluene hasn't even started evaporating off at this point. So it helps me get an idea, a head start on what components are beginning to evaporate and at what time. So all of that is due to the pot temperature that we're seeing here, which is right now above 85 degrees. All right, so that's just a confirmation of what I just told you, right? And then we're going to turn our attention to the head temperature as well. And this head temperature is also a very important temperature that I want to actively think about throughout this process. Because again, if it goes up, then that means hotter vapor is reaching it, and my fractionation is going to continue. If it goes down, then the problem is that my vapors are not reaching that thermometer anymore. So I need to increase the heat of this system so I can ensure that those vapors can reach up to the top of that Vigoroo and hit this thermometer and trigger that temperature to go up. So here's another video. This looks like a drunken Friday or Saturday night right now, but hopefully it will clear up on you. That talks a little bit about that head temperature. So what you're seeing in this image or this video is the head temperature. The head temperature is basically the thermometer that is attached to my fractionating column that sits down below. The purpose of this thermometer, though, is for me to keep track of the temperature, of course, right? So if I keep track of the temperature, the purpose in that is to figure out what temperature of that vapor is going to be. And quite honestly, at this point, I've seen a drop. The reason that I've seen a drop is because all of my first component that was coming off of that temperature has now gone away. I've really recovered everything that I can from that one. And until that second component comes off, well, there's no vapor that's condensing over, so the thermometer goes down. So whenever I see a drop in the head temperature, I normally go to my variac and I crank my variac up another 5 or 10 on the setting. Right now I'm at 80, so I'm probably going to switch it to 85 or 90. So here in the boiling flask, we're about midway through the fractionation step at this point, and as you can imagine, the volume of liquid that's in this boiling flask is getting lower and lower and lower, and that's because I'm collecting it over on the collection side of the house after it goes through the west condenser. Here you can still see it's boiling, it's still moving, it's still dripping up here at the very top. I still see the drops, and I'm still recording my temperatures, both my pot temperature as well as the head temperature. Sooner or later, I'm going to get to a point where I don't want to drive everything off, or I can't drive everything off, and that is what we call the pot sample. So at that point, I'm going to let that cool, and then I'm going to measure the volume that's left over in the pot behind. Okay, so we're about halfway through as far as collecting the cuts. I want to go back, though, because I don't want you to ever get lost in this description, in this process. When I go back to cut 7, we have to record temperatures of things, right? So this was the temperature for cut 7. Right now it's about 86 degrees. And this was the head temperature of cut 7. And right now we're looking at about 45, 46 degrees. So for cut number 7, here is the volume for that cut. And again, it could be all acetone at this point. It could be a mixture of acetone and cyclohexane. I just don't know at this point yet until I start to do some more data onto these cuts, but at least I can report some volumes at this point. All right, so after I collected cut number 7, you can record the volume. I go forever, right? I go forever for the next drip to happen, it seems like. So I begin to crank up the variac one more time. So at this point, after cut number 7, I go to a variac setting of 90. I then record the triple pot temperature, or my pot temperature there. And then I record the head temperature, which is here. And then I finally get cut number 8 off. And when I do get cut 8, there is the volume for cut 8. All right, so I don't mess with the variac at this point yet. So I record the temperature of the triple neck one more time. I record the temperature of the head one more time. Notice you see the drop. And this was a very good sign that something was getting lost. Okay, and that was heat. My Vigru column was not getting heated, and it wasn't staying hot enough. So I decided to take some aluminum foil, and I began to wrap it around just right now the top part of the Vigru. This was very cold to the touch. This was not warm at all. So as the acetone was coming off, that was fine. Acetone didn't have a problem. But maybe when cyclohexane is beginning to venture up the Vigru, it's getting toward the top end of the Vigru, and that Vigru is cold, and it's never able to get across into the west condenser, that this Vigru and this glassware needed a little bit of help. So I did decide to insulate it a little bit, and that was the point of the aluminum foil. All right, so here's a video showing the aluminum foil and kind of explaining more of that process. At this point, my fractionation has tremendously slowed down. I mean, it's taken almost 30 minutes to get my next fraction or my next cut. But as you can see in the fractionating column, I'm still getting drips, and this is closer to the boiling flask, which means that I probably need to crank up my temperature a little bit. I'll crank my voltage up on the variac. That way I can heat the heating mantle a little bit faster, a little bit hotter, and that stuff can start distilling at a hotter temperature. The problem that I'm getting right now, though, is that higher boiling point toluene and the somewhat higher boiling point cyclohexane is really taking its time to get up this really tall variac and over through the condenser. As you can see right there, it looks like a condensation ring. It's probably the condensation ring for toluene. And then as I continue to go up, I did put aluminum foil around the top part of the joint or the neck where it connects over to the condenser. So I'm going to see if that helps. It might not. But it's taken about 30 minutes for me to get my next cut. So I knew I had to do something different. A temperature change, a setting change, something had to happen, or I would be here all day. Okay, so that wasn't really good enough, actually. I had to crank the temperature up one more time, the number on the variac, and now you're seeing it set at 95. I then wait even longer. Nothing really still came over, so I had to crank up the variac again, this time to 100, and then I take a look at my boiling pot, and this is what's happening inside of the triple neck, so that way you can make those observations as you see fit in your laboratory notebook. I also want to zoom in on this area right here. It also looked like a lot of condensation was happening at the neck of the triple neck. So this was maybe some toluene that was getting up in there. I don't think I was losing it. It was just kind of sandwiched in between the joints of the glassware for some reason. And quite honestly, this is pretty common as well. So I saw it in the thermometer adapters. I'm also seeing it here. It will eventually leave. It will eventually goes to where it needs to go to. But I do see a fairly large concentration of condensate around the joint areas of the Vigru and the triple neck boiling flask. As I continue to go up the Vigru, again, I see drops that are happening in the Vigru, so I know that things are boiling. I know that things are turning into a vapor. They just haven't gotten up to the top where they need to go yet. And actually, I wait again, and there's still no drops that are happening over on my collection side of the fractionation. So I go back to the variac and I have to crank it up one more time. This time I go to about 105 to 110, and I had to keep increasing it. So I kept increasing it after that point because drops still weren't coming off, and now I'm about 115 to 120, somewhere in there. My head temperature kept going down. This was a sign that vapors were not making it to the top. I had to put more aluminum foil around the Vigru to keep it well insulated, so that way cyclohexane and toluene can make it up to the top of that Vigru a little bit easier. And finally, I get cut number 9. So here's cut number 9. Again, you can take a measurement of that volume, write it down into your lab notebook, and once more, the times of these cuts will be given to you a little bit later. All right, so after cut number 9, I get on a roll. This thing is beginning to drip like it should again. So there was a moment in time where it just slowed down. It needed a little bit of help. I gave it that help, and now it's really picking up its feet once again. All right, so I go back to my triple neck, or my pot temperature, and this is what it looks like. So again, I'm just going to have to write greater than, but this time I can also write less than, right? And this is 120 up here. I know it says 20, but if this is 80 and that's 90, I know 100 is going to have to be in here. 110 is going to have to be somewhere up in here. This is 120, 130, 140. So I know it's less than 120, but I also know that it's going to be greater than 90 or 95 as well. So I can write that into my lab notebook. Here's the head temperature. Notice it's still down. It's in the 30s. So my extremely higher boiling point vapor has not came off yet, which is okay. I'm still getting drips, and that's really all that I'm after. And then cut number 10 is here. Notice the change. There's an observational change with this one versus the others. I'm not going to tell you what that is. You can figure that out, I hope, pretty easily. But there is an observation change with cut number 10. It's kind of strange for me. I didn't really expect that to happen. And you're also going to see cut number 10 show up in a little bit different area as well in this presentation. But cut number 10 was a problem. So cut number 10, record the volume, an observation change happened. Make sure that you record that in your notebook. All right, I go back. I get cut number 11. Well, here is the temperature for the pot. Once more, same as before. Here's the temperature, though, for the head. And if I look at this, it was 30-some, but now look at it. It has skyrocketed up. So this is a very good sign that my next component or components are getting ready to fraction off, and I should have my graduated cylinders ready because I'm going to get drop. That's going to happen pretty quick over on the collection side of the fractionation. So cut number 11 is going to be here. I don't make any changes in the variac. I go back, read my pot temperature. That looks like this. I read the head temperature, which looks like this. Again, I need to write greater than, right? This is 60. This is 65. But up here is 100. So I can at least put less than that. And then here's the volume for cut number 12. I still get drops. I don't need to change anything on my variac. Here's the temperature of the pot. Notice now it has escaped that gray stopper. I can actually read the temperature one more time, way up here at the top. This is, of course, at 120. If you look at the boiling point of toluene, you would quickly understand that we are now greater than the boiling point of toluene. If you want a little bit closer look at that temperature, this is still from the pot. I've just now zoomed into the top piece of it, so that way you can make an actual temperature readout maybe a little bit better. The head temperatures here still haven't reached over that gray stopper yet, so it's somewhere in between. And finally, I've got a video that is closer toward the end of the fractionation for you. So we're getting to the end of the fractionation process. There's very little sample in my triple neck boiling flask that we started off with in the very beginning. Maybe a milliliter, 2 milliliters, somewhere in there. As you can tell, it's still dripping, which means that there's still sample up inside of the fractionating column. I did end up putting aluminum foil on the entire fractionating column pretty much, all the way up to the very top to where it meets the joint of the condenser. I'm still recording my temperatures. I'm still recording the volumes that's coming off in my receiving flask end. There's the condenser, but really what I want to show you here are the sample vials that are in the very back. We, at this point, I think are on sample vial number 15 or number 16, and there's proof that I've sit here for hours collecting the fractions as they come off in really small volumes, so that way we can analyze the purity of those fractions. So that's how many we've gotten so far. We're not yet done. We can maybe pull off another 1 or 2 more. I've also taken away the ice bath on the receiving end, and the reason is because the toluene, which is here on the later part of the stage, its boiling point is super high. So once it condenses, it's not going to really evaporate off on me. So I don't necessarily need the ice bath for the toluene cuts. I could, just to be safe, but I just didn't worry with it. The ice was melted, the water was getting colder. I've been here for hours, so as you can imagine, it was getting back to room temperature. All right, so overall, that is the fractionation setup, and hopefully you'll get your data and you'll be able to do your spreadsheets and all the calculations that come along with the fractionation lab. Okay, so we're getting closer to the end. However, I do have cut number 13. So here's cut 13 based on those previous temperatures that you saw with my head and the Vigru. So there's those. I then have still more liquid that I can reclaim and recover. So I record the temperature of the pot one more time. Keep in mind that there is a 100 in front of those numbers, folks. That is 120 and 130 and 140. So don't forget that, because we are way above the temperature for boiling point of toluene at this point. Here's the temperature of the head once more. I know it's greater than a certain number, but it's also less than a certain number, and I want to make sure I include that in my lab notebook. So cut number 14 I was able to get. Here's cut 14 for you. So there's the volume. And then with no changes at all, no changes. There was no changes in the temperatures of the pot. There were no changes in the temperatures of the head. There was no temperature changes as far as the variac, or setting changes as far as the variac was concerned. I then get cut 15 as well. It came off pretty quick, so I had to switch my graduated cylinders and put the second one up on, put the first one over to the side, and this was cut number 15 as far as the volume goes. In addition to that, this is where my fractionation begins to stop. okay? There was a little bit that was left over in the variac on the heating mantle and in the triple neck. So on that side of the fractionation, I just allowed that to cool. So any vapor that was trapped in the Vigoroo that hadn't made its way up and over yet would condense back down and fall into the pot. And then I was able to capture the pot sample as well. So once all of that cooled down, I then took in, a glass pipette, and I just sucked up the sample that was left over in the pot, and I put that into a graduated cylinder in order to measure the volume. So this is the volume of the pot sample, or the leftovers is what I like to call it. And then here we end up with a whole line of fractions that I'm then going to have to test. That's right, I've got to test each and every one of these. The more fractions I have, the more testing I'm going to have to do at the end of the fractionation process. But I've got to collect them in really small volumes, because it's up to me to get a really clear-cut, pure compound whenever I can get one. All right, so there's the pot sample. All of my samples have been collected. The fractionation at this point is now complete. So then I go on to the second half of this lab, and that is refractive index. So the question I have on the screen right now is, why run this first? And here's the answer. I've got 15 cuts, and I need to determine which of these 15 are the purest. Meaning, out of those 15, which one would be closest to acetone, which would be closest to cyclohexane, which would be closest to toluene. Well, I can do all of that on the FTIR and see what the FTIR tells me. But that's a lot of wasted time. It's going to take a long time to run all 15 samples on an instrument like that. So I need something very quick. I need something very simple. And that's where the refractive index is going to come in. So refractive index, also known as RI. So this is an instrument that we use in a laboratory. We use it for a multiple of different labs, so this does probably make sense to be put into an appendix. And I want to be able to go through and write down the directions of how to run and operate this piece of equipment, because that's part of this grade sheet, and it's also going to be part of the grade sheet for the other labs that require it as well. So I want to make sure that, number one, I want to provide enough directions on how to use the equipment so I can give that to somebody that's never used it. They can read my directions, they can make sure that they can follow those directions and not have any questions. So I want them to be that detailed as far as the directions go. And number two, I also want to include a little bit of theory. A little bit of theory of how this refractive index does its job. So here we have a prism, and there is a drop of solution on that prism, and we're getting ready to put a light energy source to it. And that light energy will hit that drop of liquid, and this drop of liquid will begin to bend that light, and that's what we call refractive index. So again, the way I like to explain this is, imagine a pool on a hot summer day. Someone's in that pool and you're standing on the edge looking down at them. The top half doesn't quite match the bottom half, and that's what refractive index is doing. It's bending the light, and molecules will bend the light in a certain way as far as the angle goes, and that is what we somewhat refer to as refractive index. So here I've got a video. I just want to play a couple of things about the video, about prepping the instrument and getting ready for running a sample. Folks, this is the refractive index instrument, and I'm getting ready to run my cuts on the refractive index, or refractometer is another word that we call it. Alright, so the way that I use this, just in case you've not used it before. Okay, so here's my prism. I'm going to open the prism up. I'll put 1 or 2 drops of my sample onto the prism that's been cleaned with acetone or methanol. I then close this prism back, and I'll take this lamp in the front and I'll raise it up to the prism. To the left hand side, I'll see a flip switch. I'll push down midway. That turns the light on. I'll look through the eyepiece. When I do, I'll see a large light and dark area to show up. I want that midway, half light, half dark. When I line it up the proper way, I'll go back to my flip switch, I'll push down, and then a meter will show up in the top. Once the meter shows up, I'll read the number that is displayed, and then I'll move on to my next cut. Folks, I've got probably 15 cuts here plus a pot sample, so I'll be at this refractometer quite a while. Okay, so something I didn't mention in the video, I told you about a light area and a dark area, and I said that this had to be in the middle. If it's not in the middle, that is the purpose of this big knob or dial to the right-hand side. I'll grab a hold of that and I will turn it up or turn it down, and that will move that dark and light area for me until I can get it into the center of the viewpiece. The other thing I also want to mention is the dial in front. This is a fine adjustment tool. And what this does is it allows me to focus the dividing line between the light and the dark area. So in order for me to explain this a little bit better, let's talk about what you don't want to see in the refractive index. So when I put a sample onto that prism, I close the prism and I raise the lamp up. I do not want to see something that looks like this, okay? The reason is because I see the light area up here and I see a dark area down here, but if you look at the dividing line, it is extremely out of focus, and this is not a very good read. It will not be a very good read for me. So I really want to see that dividing line clear cut, a very well-defined line that goes all the way across. If I begin to go to this instrument and I began dialing this left or right-handed, what I would see is maybe that dividing line getting even more so out of focus. Okay, well, that's a very good sign I'm going the wrong way. And then I'll dial it the other way. And what you'll see there at that point is if you go too far in the other direction, instead of red, it might go blue. Again, there is not a fine dividing line between the light area and the dark area. So that is something that you do not want to see either. What you are after is something that looks like this. Notice there's no red, there's no blue. This is a very clear-cut dividing line that goes all the way across. I can see that. And I want that dividing line to be right there in the crosshair. This is where I want it to be. Okay, so I'm going to take the large dial over on the right hand side and I'm going to turn it up or down in order for me to get that dividing line smack dab in the middle or the crosshairs of that eyepiece. Once I do that, I'll then go to the flipper switch and I'll flip down, and that is where the meter shows up. All right, so what I did is that I went to each cut, and we're going to start with cut number 1. Cut number 1 was collected at 11:49 a.m. I told you later on down the road I'll give you the times, and this is where I'm giving you those. So 11:49, this was my first cut that I got from the fractionation. I put it onto the refractive index. I adjust the large knob until I get the dividing line in the middle, like it is here. And then when I get it in the middle and in focus, I flip the switch down, and this is the meter that I see from the eyepiece. So I need to record what this number is. So let me kind of tell you how to read this meter if you've never seen one of these before. I first need to go to the crosshair. It's somewhat out of focus, and I apologize for that. But I need to go to the crosshair, and if you look up and down, all right, this is the number that you will need to read and report wherever it crosses that line. We're not really going to focus down here at the bottom, only the top one. All right, so if you look, here is 1.370, and here is 1.380. So let's talk about how these units are divided up, okay? So if this is 370, then that would mean this is 371, 372, 373, 374, 375. There's the tall line right there. This is 376, 377, 378, and 379, and then it goes to 38. All right, so those are the taller lines that are on that refractive index meter. All right, so that's the number one go-to that you're going to have to figure out. So if you look at this line and where it crosses, here's 375, there's 376, there's 377. It's right in the middle of that, isn't it? All right, well, these small little lines down here at the bottom, those are fives. All right, so what that means is that to the left, and let me maybe change color here. I don't know. That way you can have a point of reference. All right, so we'll draw that purple. That purple number is 1.376. Okay? And then over on the right-hand side, we'll keep that one red. That number is 1.377. Well, that small little line in the middle, it's in the middle of those two numbers. Okay, so what does that mean? Well, that means that this is 1.376. That is what those tiny little numbers mean in between the two taller ones. So if I go back, this is 370, 3705, 371, 3715, 372. 3725, 373, 37, and so forth. All right, that's how we do that. So each one of those are 0.0005s, and that's how you'll read that meter. So I will let you read this meter on your own and report the numbers that you are reading. So I would say pause it as I flip through these slides. That way you can record the proper measurements down. If you are unsure of the measurement readouts and you want to email me and let me know if you're reading it the proper way, then feel free to do so. It's going to be better if you do that than if you read the meters all wrong and then report wrong numbers for every one of them. All right, so there's cut number 1. There's the refractive index. Cut number 2 was collected at 1202. And if I ran that on refractive index, this is what I read. Next is cut number 3. Cut number 3 was collected at 1212. There's the readout for cut number 3. Cut number 4. Cut number 4 was 1218. Cut number 4, I put it on. I took a picture of this just so that you could see a pretty well-defined dividing line. But over here to the left, it kind of skewed. This is somewhat normal at times. This is a very good sign that maybe I put too much or too little sample on it. And if I went back and just cleaned off the refractive index and reapplied the sample onto that prism, then this does straighten up a little bit for me. However, I felt pretty good. The reason is I see the crosshair and that dividing line is at the crosshair. So here's the reading for cut number 4. All right, so cut number 5 was collected at 1224. Cut number 5, here was the refractive index reading for it. Cut number 6, 1228. Happened pretty quick, back to back. I'm on a roll. And for cut number 6, here was the refractive index for it. Next was cut number 7. Cut number 7 was collected at 1235, so I didn't have to wait too long for that one either. And cut number 7 had this for a refractive index. Cut number 8, 1242. Again, pretty consistent. I'm getting fractions. I'm okay with this. So at 1242, that's when that fraction was collected. I eventually ran that on refractive index, and this was the number for cut 8. Cut number 9, 1258. Again, pretty close. I'm okay with that. I've not had to wait forever, but it's been about an hour and a half since I've started. All right, so for cut number 9, here was the refractive index. Our next one was cut number 10. If you remember cut number 10, I told you write down an observation change because there was one. When I put it on the refractive index, there was actually an error. I couldn't read this in the beginning. So I tried it a second time. I still wasn't able to get a really good reading. I just put that over to the side, and I'll come back to this last. Cut number 10 was collected at 2:35. Okay, so 1.5 hours between cut number 9 to cut number 10 went by. 1.5 hours. And then I finally got cut number 10, which is that weird cut that I told you to write down an observation change for. This weird cut now is starting to cause me problems in refractive index. Why? I don't know yet, but I tried to read it. I couldn't, and I just set that over to the side, and we'll read it after the fact. All right, so then I go to cut number 11. Cut number 11 happened at 3:02. Notice the cuts are starting to happen a little bit longer apart now. I also started this process about 11:30, 11:40 in the morning, and here it is at 3 o'clock, and I was still getting cuts, and I'm still not done. So cut number 11, 3:02. Here's what cut number 11 looks like. There's the refractive index for it. Cut number 12, 3:06. So once I got these later ones, it seemed like that one almost immediately happened, didn't it? At 3:06 for cut 12, here is the refractive index. Here's cut 13. Cut 13 happened at 3:07. Folks, the last one happened at 3:06. That's how fast that cut came off. So cut number 13, here's the refractive index for it. Cut number 14, 3:10. Again, very quick. And there is the refractive index for cut 14. Cut 15 happened at 3:14. Again, very fast. You can imagine me juggling the graduated cylinders and the ice baths and different graduated cylinders and pouring them into the containers, and then on top of that taking pictures of all of those cuts too. The head temperature, the pot temperature, all of the observations, the videos. I was a madhouse at this point. So cut 15 at 3:14, and here's the refractive index for it. Not done yet though. So we also had our pot temperature, or our pot sample. The pot sample happened at 3:46. I left this cool. That's why that's a little bit later after the fact. So again, I started this lab at about 11:30 in the morning. I really wasn't finished with the fractionation part yet until 4 o'clock in the evening. So that's how long that this process took for me. Okay, so 3:46 p.m. is when I let everything cool, and I softened out the sample that was remaining in the pot, and I transferred it to a graduated cylinder, read a volume for it, and then I read the refractive index for the pot sample, and this was the refractive index for it. Now keep in mind that we had trouble with one of them. I had trouble with the 10th one. So number 10 I'm going to rerun. So now that I've went through all of these as quick as possible to prevent evaporations and so forth, I went back to cut number 10 and I re-attempted it. All right, so here are my samples lined up. And what I did is that I kind of put them in order. So spot 1, 2, 3, 4, so forth. And this is number 9 and this is number 10. So as I was running them, I lined them up this way. And I kicked this one out in front so I knew which one was which. And then there's 11, 12, 13, 14, 15, and then the pot sample. So there's all the samples grouped together into one, but this helped me remember, Tracy, you need to go back and you need to rerun number 10. And that's exactly what I did here. So that way I could go straight to it. I wouldn't get confused. I wouldn't rerun one that I've already ran. That is number 10. I need to put it back on refractive index. And for some reason, this one worked out perfectly fine. So I don't know what it was in between running it the first time to running it the second time, but something interfered with it. And by the time I got to the end of this process and reran number 10, I had no problems with that sample at all. I got a very clean division between light area, dark area, and here was the read for sample number 10. Now, I've ran all of my samples. I've ran all of my cuts, but I need something to compare those to. And I can look up the refractive index of acetone, cyclohexane, and toluene perfectly fine in Wikipedia or Merck or CRC or another online reference. It's not a big deal. However, those are textbook numbers, and they might not be perfectly calibrated to our instrument that we are using, right? It's kind of like balances. Balances will all give me a general number or an idea of where I need to be and where I am, but they will be slightly different. And this refractive index might be slightly calibrated a different way than a neighbor refractive index. So I'm going to take the time and get the stocks of the pures. And that's exactly what I did here. So I'm going to go and get the stock of the pure acetone. And then I'm going to run the pure acetone on the refractive index instrument. And this is the number that I got from that sample. So if I did that with pure acetone, I'm also going to have to do that with pure cyclohexane. So again, I go to cyclohexane. I get the pure straight from the cabinet where we order it from, but keep in mind nothing's ever 100%. I put cyclohexane onto the refractive index just to show you I still get a very nice dividing line. Notice there's a blue hue over here and a reddish hue over there. That's okay. The dividing line at the crosshair, pretty clear though. It's very evident of where that dividing line is. So I'm still getting very good data from the stocks. There's no difference in that. And then I read that value for cyclohexane, and this is what I get for it. Then last, I go and get my pure toluene. Pure toluene straight from the jug. I place that on the refractive index. And this is the value that I get for it. So now that we've got all of our refractive index reads, here's the story with it. You need to utilize these refractive index readings and see which ones become closer to the true values, because that is how I will pick the cuts that are necessary in order to run on the FTIR instrument. I'm also going to go back because it often said label information, right? Cyclohexane, you will be able to see the label here perfectly fine. And that lot number is N05E721. That is the lot number for cyclohexane. Right, now, to the left is acetone. And to the left, on the acetone jug, here is the lot number that's going to be stamped onto the side. All right, so if you look at that lot number, can't really see it here, can we? So I'll enlarge it. This lot number is going to be 43339337. Okay? So there's the lot number for the acetone. And then finally the toluene. The toluene jug we also need a lot number for as well. And if I look here, here's the label. Over to the right-hand side, I see lot that's stamped right there, but I don't really see a lot number that happens after that. All right, well, here's the story. I looked through my pictures, and I really couldn't find the side label of where I took this picture. So for this one, we're going to have to put lot number of NA. So that just symbolizes that we forgot to write it down. I didn't know it, and that's okay. I'm not going to take off points because this was something that I made the mistake on and not you. All right. In a laboratory, if you were there physically, you could go in and you could write down these lot numbers after the fact. Just go back to the same bottle that you used before. So once we figure out the three possibilities of my pures, I'm then going to turn to the Ftir instrument. And the Ftir, again, stands for Fourier Transform Infrared Spectroscopy. And I'm going to get the Ftir to confirm and identify the components that I've pulled from. So if I've pulled my pure cyclohexane, acetone, and toluene, the acetone, cyclohexane, and toluene better show up on this instrument. So here's the Ftir. Right now, I just flip the button on into the front, turn the power on. I've also double-clicked the software. That's what you're seeing on the computer screen here. If you want to know full-blown directions of how to use the Ftir, then I'm going to tell you to go back and re-watch the ethanol lab video and fast forward to that part of the video that talks about Ftir. I go through different steps of how to start this instrument up. I go through the different software pieces and everything that you need to know as far as directions go. So that way the Ftir can be placed in your appendix of your laboratory. If you do not put directions on how to use the system and software, then those are points that are taken off. And you have to have those points in there if you want really good grades, right? There's no sense in that. So write it in one time, refer to that every time that you need to use it. Review on Ftir. Again, go back to the ethanol lab. That's where you're going to find it. Make sure that directions are included in your lab notebook, so that way you can give that to someone that's never ran it, and they can read what you've written down, and they can follow your steps as they are, and not have a problem in running their samples. It typically goes into an appendix in the back, and when you scan your lab notebooks, if you're uploading these online, you want to make sure that you are also including the appendix, so that way if you're going to refer to it, I've got to see what you're referring to. If not, I can't give you points on that. So you make sure that everything is included. So I'm going to scan the pure compounds first. Right? If it can scan and identify the pure compounds, then that makes me feel really good that it can do that with my samples as well. All right, so I'm going to go and just scan pure blown acetone. This is a different acetone bottle, but it's actually the same from the main jug. That's what we use to fill up these jugs with. So it's the same jug, no matter what, same label information. It's just in a nice little squirt bottle that's convenient for me beside of the Ftir instrument. So I place that on the Ftir. I go through the directions that we did in the ethanol lab, and sure enough, it confirmed that that was acetone after I ran it. So the spectral database search allowed me to confirm that that pure was in fact acetone that was in that bottle. So that's a very good thing, right? It should have been. All right, so we're going to play a short video here just to show you a little bit of the instrument as it's running and some of the software as it's running as well. Folks, at this moment I am running acetone pure on the Ftir instrument. So it's in the process of running right now. It's not yet finished, but once it is finished, I'll go up to the top toolbar and I will search this infrared spectra that shows up on my screen. That way it can cross it in the database and it will tell me what that compound is based on its decision. So once again, the only thing that I have done in order to use this complicated piece of equipment is just to put 1 or 2 drops on the ATR attachment that you see there. I'm keeping an eye on it just to make sure it doesn't evaporate off, and it's behaving itself as of now. So it will keep scanning this. It will scan it 40 some times, and then the database will pop up so that way I can search it. What you see on the screen right now is the infrared spectra of acetone, and I will say it looks very, very good, and it should, because it's a pure compound. However, one of the things that I want you to not forget about when you run samples yourself is don't forget to name them. A lot of people forget to do this, and I actually did it on the first one myself. So when I say don't forget to name them, what do I mean? Well, up here in the very top of the screen, you're going to see an area here that says sample name, right? So that sample name needs to be changed, and this one I did catch. So I changed this one to Cyclopure Frac TH, so my initials, Fractionation Lab, and I identified it, that it was Cyclohexane Pure that I was getting ready to run. That's only one area, though, that can be changed as far as sample name. If you look to the left of that, so here's sample name to the right, okay? If you look to the left of that, under file name, you can also name it specifically there as well. And this will be a very quick reference to me, so I know exactly what that file name is supposed to represent. And I normally name them the same. So Cyclofrac TH is what I named that one. Probably should have put pure in there as well, but I didn't. So 2 areas, file name and sample name. Then when you do that, right, up here's the top of the monitor, there's the top of the software, here's the file name that I've changed, here's the sample name that I've changed. I then can go up here to measurement, and then I can start to measure my samples, all right, or sample scan, or background scan, or monitor, depending on what I need to do with those particular runs. So that's just a way that I can identify them into a database that is getting larger and larger every single year. So after that was ran and analyzed, well, sure enough, it told me it was cyclohexane. It's right there. Number 1 spot, score of 913, spot number 1. Next was my toluene. Here's the toluene jug, and that toluene was ran on the FTIR as well, and this is what it told me for toluene. Okay, it did not identify toluene the right way. I'll go ahead and tell you that right now. Okay, here's why. What it did identify it as is ethylbenzene. See the 656, only one other beat it out, and that was polystyrene. All of these are very similar in structure. Ethylbenzene is a benzene ring that looks like this, but an ethyl group, a CH2 and a CH3. Toluene is a group that looks like this, a benzene group with a methyl group on it, just a CH3. Do you see how close those are? Polystyrene is the same way. Polystyrene would be a carbon that has a double bond here to another carbon. All of these are very structurally similar, and sometimes it's very hard for the infrared to be that exact. Right? It's getting in the ballpark range. The only difference is 1 carbon difference. That's it. So this I was okay with. Not a problem. It identified it close. Not exact. But it did give me the benzene ring. It just gave me an ethyl group instead of a methyl group. 2 carbons instead of 1. Whatever. No big deal. I'm not worried about that. So that I was okay with as well. All right. So I identified the 3 best cuts for my refractive index. Remember, the pot cut can also be included in one of those. Any of them are fair game. So I took out the 3 that I thought was best suited, and I analyzed those 3 samples on the FTIR just like I did with the pures. And those I do not have pictures of. However, you will see those infrareds scanned and uploaded into the lab folder where you found this video. So that way you do have that lab data to reference to, okay? Finally, one of the other things that the grade book is going to ask for, their grade sheet, is the SDBS. All right, so what is the SDBS? Let me pull that website up so that way you can see it. So most of the time, I just go to Google and I type in SDBS for Spectral Database System, and this is the link that pops up here in the very front. That's the link that I want. I also have this link in Blackboard in the course folder. So if you don't want to go through this route, you can click on that course folder and it will give you a direct link on what to do and how to get there. So I'm going to click on that link. That link is going to direct me to a website. I agree to the disclaimer that I'm not using this for profit. I'm not going to use their research work and their grant-funded work to basically sell something. So here's the screen. It's a pretty simple kind of basic database search, and I want to type in cyclohexane. All right, so I'll just do cyclohexane first. I'll type that compound name in, and then down here at the bottom, I'm going to hit search. I could type in acetone here. I could also type in toluene there as well. I normally do my searches through compound name and not through molecular formula or molecular weight. I just think it's easier to search by name versus some of these other ways. It's just so many different ways to enter things in. A name is a pretty clear-cut way to search for something. So then I hit search. When I do that, it's going to search the database. Cyclohexane and anything with cyclohexane's name will pop up. You'll see this with acetone and toluene as well. But cyclohexane is what I need, so it's the very first one. If I see Ys that are here, then that means yes, it is in the database. And then if I see Ns, then that means no, they do not have that in a database. So I'm looking for the infrared, and there's the IR. And under cyclohexane, I see a Y, so that means they do have it. So I'm going to click that Y, and then this will pop up the textbook image of what cyclohexane is supposed to look like. And that is what we call the SDBS infrared that we need to print and save and put into our laboratory notebook. Normally from this point, what I normally do is I right-click, and I either save the image or I copy the image and then I paste it into Word or Excel or whatever I'm deciding to use. Sometimes, though, this will give you a forbidden image error code, and if that's the case, then you just need to print screen. So there's a button on your keyboard that says print screen on it. You hold down, I think, typically the control button, and you hit print screen, and that will save everything on your screen so that way you can paste that into a document. So if you don't know how to do that, just Google print screen, and then it will show you step-by-step directions on how to do that with your keyboard. All right, folks, so this is 1 hour and 40 minutes. 1 hour and 40 minutes of a discussion of a lab that really took me from 11:30 in the morning to over 4 o'clock in the afternoon on the first day. And then the second day, I came back to do the FTIR runs and some of the refractive index runs for the pures. So 2 days, I think, is a pretty fair game to sit in on an hour and 40-some minute lecture, and you can call this lab finished at this point. So this lab is going to have quite a bit of calculations, and it's also going to have major spreadsheet work with it as well. So you want to go through and take a look at that video as well. I'll give you an example of the template that I would like for this fractionation to fit in, so that way you can use that as a guide for all of the calculations that you have here. So the ultimate goal here for this lab is to report the number of milliliters of acetone that we have recovered, of cyclohexane that we've recovered, and of toluene that we have recovered. And I know how much I've used in the very beginning, and hopefully we can get that back. The total amount here was 50 milliliters. So 50 milliliters is the total amount of sample that we started to heat in the very first part of the process. And hopefully, after I add up all of the volumes of the fractions, I will get something to close to 50 milliliters as well. It won't be exact. I'll lose some, and that's okay. Not a big deal. But hopefully, I'll get really close to the 50 milliliter mark. Throughout this process, the refractive index is also going to allow me to calculate percentages of each one of these in the cuts. And then the FTIR, of course, is going to confirm the cuts that I pulled as the purest ones. So a lot of lab data. So this is the next half of the lab that people hate, and that is the calculations. That's the spreadsheet that comes along with this lab. But again, all the other ones, not so much. This one seems to be problematic, and that's why. So we make it through fractionation. That's all right. We make it through fractionation. we actually will do fractionation again in the program. I hate to burst your bubble, but we will. And if you're taking a proper organic class, you'll also see fractionation in there too. So it's something that we can't ever get away from, but it's something that we need to accept. When it does happen, we just need to prepare for it. We need to move our schedules around to make sure that we have enough time to do this lab and to do the calculations that come along with the lab as well. So with that said, I am now stopping. 1 hour, 45 minutes into it, I have given you all the data, all the observations, all the temperature reads, all the volume reads, all the FTIRs and refractive index reads that you need for this lab in order to finish it up. So once more, if you've got questions, you know how to get a hold of me. Good luck on the fractionation. I'm sure that you will have questions, so don't be timid to ask me for help. And with that said, that is where I'm stopping this video. And then we'll just keep trucking on. We'll keep forking out one lab after another, so that way we can finish that in our lab notebooks and get this class finished.